Good afternoon, everybody. Thank you for coming. My name is Guangchi Xing from Penn State. Today I'm going to talk about the multiparameter viscoacoustic FWI. A major problem of this task will be the crosstalk. We are trying to recover both velocity and attenuation models at the same time, but the velocity and the attenuation are intertwining with each other, just like the yarns in this picture. So how to untangle this mess would be the major challenge, and it is the primary motivation of the study. Let's start by illustrating what exactly the crosstalk is, using a simple 2D example. These are our target models. The left-hand side is the velocity, and the right-hand side is the Q model, namely the attenuation model. We use them to generate the observed data. Each of them has a homogeneous background and a circular anomaly right here and right here. We have a crosswell aggregation system with the source on the left edge and the receivers on the right. Starting from the homogeneous initial models without these anomalies, we can calculate the gradient for both velocity and attenuation. Here we use the gamma as a model parameter instead of q to represent the attenuation, and the gamma is roughly proportional to 1 over q, and these are the gradients we got. Here we show the negative gradient. In the gradient-based FWI algorithm, these are the update directions, or the search directions at the very first iteration. Delta m is the model update, alpha is the scalar called the step length, and g is the gradient. We can see that the velocity gradient is doing a pretty good job capturing the velocity anomaly, and the gamma gradient captured the attenuation anomaly as well. However, the velocity anomaly is mistakenly mapped to the gamma gradient. This is the so-called crosstalk problem, where the data synthetic residue introduced by one model parameter is mistakenly assigned to another, and it is one of the major challenges we are facing in the multiparameter inversion. The gradient-based method relies on the gradient, of course, which is the first derivative of the objective function with respect to model parameters. One of the potential recipes for the crosstalk issue would be to incorporate the second-order information, namely the Hessian, denoted by the letter H. In this Hessian-based method, or the so-called Newton's method, the search direction equals to minus H inverse G. Now let's move on to talk about the Hessian, about what it looks like and what kind of information it has. To begin with, Hessian is an nm by nm square matrix, and it is symmetric, where nm is the number of model parameters. And each element of Hessian, hij, at row I and column j, can be written in this form, where mi and mj are two of the model parameters, u is the forward wave field, and delta d is the data residual. Here we ignore the time integral for simplicity. The second term is generally pretty small, and it is usually ignored. So now let's forget about it for the time being. The first term is the so-called Gauss-Newton approximate Hessian. Now let's talk about what it physically represents. For example, we consider a 2D model with the source right here and the receiver right here. Mi and mj are two model parameters. Say they are velocities at these two locations. Basically, u is the regular wave field excited by the source. So partial u over partial mi will be the scattered wave field induced by the velocity change at the mi location. In other words, the background wave field u travels from the source to mi, gets scattered by it, and the scattered wave field partial u over partial mi propagates from the mi and recorded by the receiver as a spike right here. And the same thing for mj. In this example, the mj's wave path is shorter compared to mi, so the arrival of the mj scattered wave is earlier than mi. According to this equation, the Gauss-Newton Hessian is basically the zero-like correlation between these two scattered waves. We assume that the source time function, or say the wavelet, is perfectly delta function pulse. Then, aside from the multipathing scenario, the correlation, namely the hij, is generally zero, unless mi and mj coincide with each other. like this one. As a result, the Hessian has non-zero values only on its diagonal, where Mi and Mj are the same point. So the Hessian is a diagonally dominant matrix. But in practice, the wavelet is never as perfect as a delta function. Check out the waveform here. So in practice, both scatter waveforms will be spread out a little bit. Then to have a non-zero value in the Hessian matrix, Mi and Mj do not necessarily coincide with each other. Instead, we will have non-zero Hessian values as long as Mi and Mj are neighbors. See the waveform. As a result, the Hessian will be a banded and striped matrix, and the pattern depends on how you sort the grid points. Then let's talk about what kind of information is carried by the Hessian matrix. As we just mentioned, we can tell how the scattered waves generated by neighboring points correlate with each other, so we have the information of the finite frequency effects in the Hessian. Now let's consider the case when Mi and Mj are the same points, namely the diagonal element. If we move this point right here, on the trajectory between the source and the receiver, check out the waveform. And then the wave travels shorter. The arrival will be earlier. And also, there will be less geometric spreading, so the amplitude will be larger, and the Hessian element will be larger as well. In another word, the values of the Hessian elements can indicate the illumination information, which captures the source-receiver geometry. So far, we have only discussed the monoparameter case. So what about the multiparameter FWI? For example, in the viscoacoustic case, if we consider both velocity c and the attenuation gamma, the Hessian matrix will have a 2 by 2 block structure. The diagonal blocks are pretty much the same as the monoparameter case. Let's focus on the off-diagonal blocks. In particular, let's consider the element on the diagonal of an off-diagonal block. Then Mi and Mj represent the velocity and the attenuation at this specific point I, respectively. So Mi becomes Ci and Mj becomes gamma I. Partial U over partial Ci is induced by a velocity scatter, and partial U over partial gamma I is induced by an attenuation scatter. This Hessian element Hij is a zero-lag correlation between them, meaning how similar they are with each other. So a large value in the off-diagonal block means that the velocity perturbation and the attenuation perturbation can produce similar seismic waveform perturbation, and thus it is difficult to tell if the data residual should be attributed to velocity or attenuation, which leads to the crosstalk. So the Hessian matrix has the crosstalk information. Finally, let's check out the second term of the Hessian. Physically, it represents the wavefield first scattered by Mi and then scattered by Mj, weighted by the data residual. So in this way, this full Hessian contains the information of the second order scattering. Basically, these are the four pieces of information carried by the Hessian matrix. Now let's talk about the pros and cons of the Hessian. In the Hessian-based method, the search direction is determined by the negative gradient preconditioned by the inverse Hessian. Through this preconditioning, we anticipate that the search direction delta m can get rid of the artifacts generated by all the effects, namely make the image sharper, balance the uneven illumination, mitigate the crosstalk, and also demultiply. And that sounds fantastic. However, the most fatal problem of the Hessian is its formidable computational load. We know that it is an Nm by Nm matrix, and it is huge for a pretty generic model. It is generally beyond the current computer capacity to invert it or even to just store it. But the good news is that we have a workaround. Instead of directly computing the H inverse G, we can come up with a method to approximately solve H delta m equals to minus G. Now let's move on to the algorithm section to talk about that into detail. Intuitively, at each iteration, we try different delta m until the left-hand side approximately equals to the right-hand side. And actually, we can do much better than this trial and error method. In particular, we adopt a framework called the Newton CG, also known as the truncated Newton's method. So at each iteration, we have an inner loop in which we use the conjugate gradient method, the CG, to approximately solve h delta m equals to minus g. To make sure the computational load is reasonable, this method requires computing h nu in an efficient way for an arbitrary model space vector nu. In this study, we'll use the second-order address state method, and now let's talk about that. To give you a recap, let's talk about the general first-order address state method, which is used to compute the gradient g. Basically, the gradient can be computed in 3 steps: a forward simulation, an address simulation, and the interaction between these two wave fields. This first equation describes the forward wave field simulation, where the L is the wave propagation operator, U is the wave field, and F is the source. In this study, we use the fractional viscoacoustic wave equation. I'm not going into too many details about this equation and just present it in this abstract form. In this equation, the wave propagator L can be decoupled into 3 terms. L0, the classic lossless acoustic propagator, L1, the dispersion character, and L2, the dissipation character. This wave equation incorporates the seismic attenuation using L1 and L2, which are featured by the fractional Laplacian operators. For example, in the 2D model, we have a source and a receiver. Using this equation, we can simulate the forward wave field with the propagator L. We have the dispersion captured by L1 and the dissipation captured by L2, which leads to the reduction of the total energy. The second equation describes the adjoint wave field. L star is the adjoint of L, lambda is the adjoint wave field, and D is the observed data. R is a sampling operator that samples the wave field U at the receiver, so its adjoint L star becomes a zero padding operator. In another word, this right-hand side, or the so-called adjoint source, has only non-zero values at the receiver. Last year, we have demonstrated that while the forward wave field U starts from the source and propagates all over the place, the adjoint wave field lambda shrinks to the location of the receiver. And also, since L star equals to L0 plus L1 minus L2, the adjoint wave field preserves the velocity dispersion because of this L1 term, but instead of attenuating, it is compensating or anti-attenuating the amplitude because of this minus L2 term. In practice, we simulate the adjoint wave field in the reverse time mode, and with the same simulator as the forward one. Finally, we take the interaction between these two wave fields according to the third equation, and we get a gradient g. So this is the adjoint state method for the gradient computation. Then let's move on to the second-order adjoint state method to compute the Hessian vector product h nu for an arbitrary model space vector nu. To illustrate, we consider the case where nu has only one non-zero value that represents a velocity perturbation right here. Similarly, the computation of the h nu can be formulated by 5 equations. The first 2 are the same, simulations to get the forward wave field u and the adjoint wave field lambda. The third equation is to simulate the second-order forward wave field nu2. The source shown on the right-hand side is the interaction between nu and the forward wave field u. Since nu only has non-zero value at this location, the source only has non-zero value right here as well. So nu2 is the wave field excited by the scatter. Next one is the second-order adjoint simulation. Its adjoint source has 2 terms, so we call them part A and part B, and consider them separately. The source A is r star r mu2, which means the mu2 sample at the location of the receiver and the other points equal to 0. So mu1a shrinks to the receiver just like the lambda. Part B of the adjoint source involves the interaction with nu, so again it only has non-zero value at the scatterer, so mu1b shrinks to the location of the scatterer. Next, the Hessian vector product h nu is made up of 3 wavefield interactions. We call them h nu1, h nu2, and h-3 respectively. The first one is the interaction between the U and the mu1. We first consider part A of the mu1. So U propagates from the source and the mu1A shrinks to the receiver. Hence, the h-1A has the sensitivity between the source and the receiver. And we record this part of the contribution in here at the bottom. As for part B, still the U starts from the source, and mu1B shrinks to the scatterer. So h-1B is this fish shape connecting the source and the scatterer. Similarly, we leave the result right here. The second term is the interaction between mu2 and lambda. Mu2 is excited by the scatterer, and lambda has the hadron source as the receiver. So h-2 is sensitive to the structure between the scatterer and the receiver. Finally, h-3 is the interaction between U and lambda, and then interacted with nu. Since nu is only non-zero right here, so the last term, h-3, only has non-zero value as the scatterer nu. And we can put together these three terms, or actually four terms. And here we got the Hessian vector product h nu for this nu. Note that this is the velocity part of the product. If we take the interaction in a different way, we'll get the attenuation part, or say the gamma part of h nu in a similar fashion. We validate our result using the final difference method. As we know, the h nu can be approximated by a gradient difference between the perturbed model m plus nu and the original model m, as long as the perturbation nu is sufficiently small. So we compute the h nu using the second order hadron state method, the AD, as we just described. And we compare the final difference results, the FD, shown in the second row. The residuals are in the third row. We can see that we only have some minor residuals at the singularity points, which validates our second order hadron state method to compute the Hessian vector product. The additional cost for this method is 2 simulations per source, which is pretty reasonable and practical. So now we can put together our Hessian-based viscoacoustic FWI algorithm. At each iteration, we compute the gradient G using the traditional hadron state method, and then we use an inner SEG loop to approximately solve h delta m equals to minus G. In particular, the h delta m computation is conducted by the second order hadron state method. After we got a satisfactory search direction delta m, we conduct a line search and update both model parameters until the model is converged. Now let's get back to the example I mentioned at the beginning of the talk. Here are the target models for velocity and Q values, with circular anomalies at different locations. When we adopt the Hessian-based method, this is the update direction at the very first iteration. So it is the final product of the inner loop at the first outer loop iteration. Let's compare with the gradient-based method. So this is a gradient-based, Hessian-based, gradient-based, Hessian-based, gradient-based, Hessian-based. So the velocity direction gets sharper. More importantly, the crosstalk in the attenuation direction is significantly mitigated. Here is the final model after 20 iterations using the Hessian-based method. Let's compare with the target model. So this is the target model, final model, target model, final model, target model, final model. And it looks fairly good. The distortion of the anomaly is basically due to the limit of the source-receiver geometry. The sources are on the left-hand side and the receivers are on the right-hand side. So the horizontal resolution is not as good as the vertical one. The inverted anomalies are better than they are supposed to be. If we add more sources on the top and the receivers on the bottom, this is what we got. Let's compare with the target model again. So this is the target model, final model, target model, final model, target model, final model. And there's a little bit of directionality for the Q model, but the result looks pretty good. We have a very nice delineation for the anomaly features of both velocity and attenuation, and the crosstalk artifacts are basically gone. Some key takeaways. In this study, we developed a Hessian-based viscoacoustic FWI algorithm based on the fractional viscoacoustic wave equation. This algorithm incorporates the Hessian via a Newton CG framework. At each iteration, it uses an inner CG loop to approximately solve for the search direction. In particular, the Hessian vector product in the inner CG iteration is provided by the second-order adjoint state method, and our preliminary results shows that the crosstalk can be significantly mitigated. Finally, I would like to thank the DOE and the NSF for funding our project. With their financial support and the help from Hessian, we anticipated we can untangle this mess of yarn into a clean velocity model and a clean attenuation model. And that'll be all for my presentation. I'll be happy to take some questions.